Yeah, let's go ahead and get started back.
Okay. Okay. So for those that
another media from HMV, Hollingworth and Voss. I'm sorry, Hollingworth and Voss. And this is a nanofiber media, but the novelty here is in the structure of the media itself. You can see the folds in the media. This gives the media both strength and also added collection capacity. Below that are metal fiber and sinter metal filters.
Excuse me, is it Teal Park?
Mostly liquid applications. What's the nice thing about metal fibers is that
he's presenting somebody else. There we go.
Okay, you set an open mic.
Yeah, I can honestly say I've never had that happen before. Dual meetings.
I thought he was going to show us something really interesting.
Well, I was waiting for it, but then it became apparent.
Yeah. Go ahead, Mike. You were saying.
But okay, so you've got Mike and Mike now. So for those that don't know me, I'm Mike Sansucci. I support the Biological and Physical Sciences Division of the Science Mission Directorate for NASA. I am the Physical Sciences Portfolio Scientist at Marshall Space Flight Center. So our interests are more in reduced gravity experimentation that can be done to understand the material science or fundamental physics involved in maybe some of these additive manufacturing processes. So right now, as you heard earlier from Craig and Kristen Van Vliet, Craig Koendrat and Kristen Van Vliet, we are just kicking off a decadal survey process. So that decadal survey will be used to help drive and guide future NASA research. So right now we're soliciting white papers. I'll post the link in the chat to the decadal survey website, but just to kind of talk about things. One thing, I mean, like I said, we're looking at for the science behind a lot of this. So some of this can be enabling for a lot of these applications that were discussed today. So it's, for example, the mix experiment, that was a great example. Professor Radlinska studied solidification of cement in space. So I guess I'll just pose a general question. What are some of the underlying science that you see, the audience sees as missing in some of these additive manufacturing processes for space-based applications?
Well, hey, Mike and Mike. This is Bob Hires. Good to see you. So we got a long silence, so I'll throw one out there. Control of powder, making it go where you need it and not where you don't need it, and then getting it out after.
Absolutely.
That's on the ground. It clearly relies on 1G. In reduced gravity, the processes we're used to using may not work well or may not work at all. And for spaceflight, the processes we use now will not work at all.
Right.
I would like to second that motion. This is Otis Walton. I'm going to be giving a talk tomorrow on the effects of cohesion and scaling rules for how gravity effects and cohesion effects are changed on the moon in relation to each other compared to what they are on Earth. You need to make some things 6 times larger. Other things you need to do quite a few other changes to when you change gravity if you want to get things to move.
Yeah, absolutely. So as far as control of powders, I mean, some sort of something to pull them, maybe a vacuum to try to pull them.
Well, this is where we should not be talking about if you're in the context of the decadal survey. You should be posing big questions and not solutions. Solutions go to the NRA.
True.
There is a question related to powder flow that is more related to asteroids than to lunar, and this is something that might be appropriate for the decadal survey, and that is that Stan Love mentioned that you could form granular dust bunnies, and he did this with sugar and salt and with coffee and a few other millimeter-sized particles on the space station. He did these in Ziploc bags and showed that you could have a strength to that. There's an issue if you try to do pneumatic transport at low density. This is a technology question more than a science one, but if you try to move things through a pipe at very low velocity, there's no saltation velocity limit for transport. So you'd think that pneumatic transport would be great on an asteroid. You could just move it around with just a little tiny bit of air. You could move things very easily. However, if you get tribocharging and you get these dust bunnies, if you like, or they're a gel will form and it will jam it. We don't have any idea what kind of effort it would take to break the gel. What could you send vibrations or pulses in the transport? So it's a technology question of if you had a granular gel with 70 micron particles like you would have for regolith that filled a small container or small transport pipe, how would you break up that gel? Can you do it by pulsing the flow? Can you? How strong is the gel? What are the properties of it? Stan measured it by squeezing in his fingers, and he made estimates of strengths of his dust bunnies, as he called them. But we have it's like a protoplanet, if you like, except that with an atmosphere, you may have ways of breaking it up, and it may densify differently when you have transport. But that's a fundamental physics question that affects technology.
Right. Would there also be some complex fluid physics aspects to that question?
I think there could be, yes. It depends on whether you're using a gas and what the Knudsen number is of the density of the gas that you're using. Because if you're doing it on an asteroid, you'd be at low density gas as well. You'd want to use the minimum amount of gas to move things. If you're trying to move something from one area to another, so you'd have low density gas, and so there would be some fundamental questions about how dense does that gas have to be. Have to get the mean free path of the gas smaller than the gaps between particles and things of that sort. So there are lots of fundamental questions that could address that. I'm sorry.
And you also have to get your gas back and use it again tomorrow.
Yes, you need to separate them. Yes, because you don't have a source for it. So
good point. Yeah. Interesting. So I'm going to pick on. Oh, go ahead. Continue, please.
I was just going to say another thing in terms of moving powders and cohesion and gravity scaling. Moving material around on the moon will have a different relationship with friction and cohesion than we have on Earth. And you may find, because friction is down by a factor of 6, because rho GH is down, so the normal forces are all down by factors of 6, that you could use vibrating troughs or to move things, or a drag chain conveyor, for instance, that just pulls things along, and they're limited by friction and they're relatively inefficient on Earth. But on the moon, gravity being a factor of 6 lower, the relative efficiencies of using some mechanical systems that aren't a screw feeder or other thing that may be more reliable than a screw feeder, but may be more efficient on the moon than here. Things we have that we sort of reject. Oh, I don't want to use a drag chain because there's too much friction, or I don't want to use a vibrating trough because we've got to lift the stuff up and move it. Well, lifting it up and moving it is pretty easy on the moon. So there's some simple little technology questions that could be addressed if we look at the appropriate scaling.
Yeah, absolutely. Good points. Does the abrasion of the regolith come into play with some of these processes you mentioned?
Well, I think it certainly does. If you anything that has a small gap where you're going to be rubbing and getting a high normal force, it's a very abrasive material, and so recent SBIR, we were looking at trying to use a screen on the wall of a screw feeder, or a screw conveyor, as a way of screening material. And we found that the only way we could reliably do that, to do the sieving in the wall, was to make the gap extremely small. Well, if the gap is extremely small, you're rubbing against the screen, and it's probably so abrasive it wouldn't be very viable on the moon because you couldn't check it regularly. So we ended up talking ourselves out of a phase 2 by the time we got our phase 1 results done. But nonetheless, we learned a lot about how thick the shearing layer is outside of an auger moving, and it's very few particle diameters outside of the auger when it's shearing. So you had to make that auger very close to the wall, or you had to have a flexible material for the auger, or a compliant material. And again, neither of those would be very viable on the moon because of the abrasion.
Yeah, absolutely. Good points. So I'm gonna hopefully get some help from Jennifer. When we spoke, that was a few weeks ago. I asked some questions about processes to extract, say, metal from regolith, and your comment, I believe, and please correct me if I'm wrong, was, that's one issue, but the next issue is what do you do with it after that to make it a viable feedstock material? Can you expand on that some?
Is this question for me?
Yes, sorry.
Okay, sorry. Right now, we've got a cooperative agreement notice with Mississippi State University, and one of the grad students there is working on taking some of the metals extracted from Martian regolith using ionic liquids and creating metal alloys out of it. He tried doing it just as the metals came out of the ionic liquid extraction process, and it turned out that a lot of the magnesium that was in there, it was in too high abundance to make a really good material. So we know that we're going to have to separate the metals a little bit more than that, be able to filter out some of that magnesium, and from that we can mix it with carbon and create an actual alloy that we can use for casting or 3D printing or other processes like that. So there's a purification process. There's a process to recombine the elements and make sure they're in the right state that we need. This is especially important in things like cementitious materials. If you need to get the reactive materials in cements to do what they need to do, you have to have that specific reactive component. So you have to manufacture that, and then you have to, produce it in high enough quantities that it's actually going to be a viable process. I mean, it's good if you can demonstrate the process, but you have to make sure it's scalable so that we can get the material that we need. It has to be economically scalable. The cost is a major factor. And then be able to prove that whatever you produce functions the way that you want it to, has the strength that you're expecting out of it, and can perform in a lunar environment, in a reduced gravity environment, or, if it's exposed to the lunar surface, it has to deal with radiation and, dust and, all kinds of things. So there's this there's a lot of steps in the process between getting the extracted material and actually doing something with it. I hope that helps.
Yeah, that was very helpful. Thank you. Absolutely. So I just wonder, I mean, I guess it's process dependent, but what's extracted out of the process, how not useful is it? So does it normally extract pure elements, or Is it
I mean, it really depends. I know that if you use the ionic liquid process, typically you're able to electrochemically plate out different elements by using different voltages. If we're talking about something like carbothermal reduction, and honestly, I don't know how efficient that process is, so you might be getting out some kind of metal powder or metal sludge that might still have a little bit of oxygen in it. That's one of the things that kind of worries me about just processing these things in general, is how efficient are they really? How fast can we go through these processes, and are we going to be able to produce enough material on the output side to be useful in things like construction or outfitting, because we're going to need large quantities of materials. So scale up is a big issue.
Yep. So that's one of those things where the different processes have different strengths. So, with the ionic liquids, I've seen gram scale experiments that run days, but I haven't seen anyone scale them larger than that. And they talk about current densities that are tiny, amps per square meter or something. And in industrial electrolysis, like producing aluminum, they're about 1 amp per square centimeter, 10,000 amps per square meter. And so that's one of the metrics. FFC, they keep, or for 20 years, they've been saying next year we're going to make tons and go commercial. Maybe this is the year. And molten oxide electrolysis is pretty new, but they're building big machines now. And I'd have to look at their press releases, but it's tens of thousands of amps.
Well, that's true. But with the ionic liquid processes that we're talking about, these are lab scale type processes in terms of like current density and things, right? So we're not even trying to even go there necessarily. We're just looking at selectivity towards maybe a particular species depending on the process.
Yeah,
and that's really depending upon the ionic liquid process we're selecting for whatever we want, right?
And
but ionic liquids are used commercially, like they're used commercially in metallurgical extraction technologies.
So this just goes to Jennifer's question, which was, can we make tons of stuff? And some of the processes, people are already making tons of stuff, and some of them maybe someday. Some of those have made a lot of noise without a lot of success, and others are at different stages of the development.
Good points. Absolutely.
And then as for the form factor, if the product is solid, then you end up with powder of some sort, or else you can have an integrated step where you're plating out metals. That's what you're describing the ionic liquids, right?
Well, here it's like, so if you think about in like just the like carbochlorination processes, right? On the back end of that, and this is old process. Like there was this reactor, and it took them years to go do it. And it's what they're doing there is they're extracting aluminum, and they're electrochemically plating, the aluminum out in a molten salt. This molten salt is fairly hot, like 600 C and stuff, because you have to, in order to plate these aluminum chloride salts, you have to run it that high. Like in ionic liquids, though, and this is very old, before ionic liquids were even introduced. That's actually one of the oldest ionic liquids, is to make aluminum trichloride and to plate those out. So even in that sense, I mean, if you just got the Alcoa reactor basic bipolar design, and you say, well, hey, guess what? We're not going to run it like 500 C, and you use the ionic liquid to plate it, that process now becomes a lot more manageable, because aluminum trichlorides and other metal chloride salts, right, are volatile. And you can't just in an automated sense like condense, aluminum trichloride, which sublimates 180 degrees Celsius into a molten sodium chloride, lithium chloride eutectic mixture.
So let's go back to the question. So then with that process that you described, you end up with plating that you could imagine growing to be thick like copper cathodes, or you end up with dendrites depending on the current density. And
in that process, the aluminum actually is continuously falls off of a graphitic electrode. Like, it does not stick very well, and then it's recovered and filtered out.
Yep.
So it would work very much like that if you wanted to go that direction with it.
And if you want to make liquid, then you get liquid, and what you do with it afterwards is a separate decision.
Mm-hmm. Like, that's the way I look at it. It's propellant, it's feedstock for whatever you wanted to do, because it's aluminum, right? So
liquid metals aren't great propellants. They're kind of hard to hang on to. But so you'd freeze them, but you might cast them in situ.
Right. In that process, they would be solids in that sense, right? Because you're running at like room temperature.
Yeah.
So you have to kind of filter out the particles, right? And then you'd have the aluminum pellets, let's say.
Okay.
That's the way I envision it.
Jennifer, did you get the answer to your question? It seems like we're having a lot of conflict over whether to talk about one process or several.
Sorry, I did not mean to steer the conversation here. I think about these things quite a bit, so I wasn't trying to steer it to a bad direction there. So,
well, it was Jennifer's question. Did you get what you needed?
Oh, yes, I did.
Okay, thank you.
Okay, so anyone else have any let's see, processes we could discuss? What are the big Mike, what are the big problems you see in surface construction?
Well, I've referenced some of them, or earlier in the discussion. There's variability in regolith composition. There's kind of the unknown unknowns. When we're not likely to do a lot of large scale processing with high end, agglutinitic simulants. So will there be, will problems present themselves on the surface that we didn't really test thoroughly enough to, because we couldn't afford to test thoroughly enough to. Those things concern me. That the thermal environment is a huge. Dust. The dust is a big issue in terms of hardware development. Protect you. There was a lot of, some of it is kind of more anecdotal than others, but there was a lot of damage to Apollo hardware during just the few days that they were on the surface. Rover wheels were damaged, radiators, helmets, gloves, elbows and knees of spacesuits were, multiple layers were eaten through by the dust. Not eaten through, just abraded. Tremendous damage. And in those missions were what, 3 to 7 days or something like that. Yeah. I should know that, actually. I was alive then, but it's a little bit unnerving to think that now we're talking about going for weeks, because I just don't know if I see enough development in hardware capabilities to support those longer missions. Required power is going to be big.
Absolutely.
The temperature extremes are going to be big. Any construction material at the pole that's got to survive, the not just the high temperature or the low temperature, but the transitions, repeated transitions from high to low, tremendous loading, mechanical loading on materials due to contraction expansion. There are some zero or negative coefficient of expansion materials that are out there that we're looking at for construction, but they're not trivial to make. So those are the things that kind of keep me up at night.
Yeah, absolutely. Yeah, I understand that.
But I'm always
Um,
interested in, I'm always, and the, I mean, I feel like I'm very comfortable with understanding the need for a landing pad, but I'm not at all comfortable yet with knowing that materials that we're looking at or testing yet are going to be able to withstand that environment. It's one thing to build a pad if it works every time. It's another thing if you build it and then every time you use it, you have to go back and make significant repairs to it before the next guy can land.
Yeah.
That doesn't. The moon is just too harsh of an environment to have to go out and do that all the time. So
Right. Looks like there was a raised hand. Don.
Yeah, this is Don Barker. Michael, those were interesting comments. I'm lead architect for the XEMU right now here at JSC, and we are knee deep in the dust issue,
Yeah.
so to speak. I'm in fact writing a huge test and evaluation document right now for all of our components on the spacesuit. So I totally agree with that. I think that's going to be one of the biggest issues that we have. Other issues, kind of like you touched on, materials in the environment, especially if we ever access a PSR type environment. I think that is a big unknown. I think we're okay if we're kind of in a standard Apollo type environment for most cases. But for anything with longevity or sustainability, understanding the dust environment and tracking it in and out of vehicles, et cetera, is very important. Right now, we're dealing probably with a one crew environment inside the vehicles, kind of like Apollo, even though we haven't got any final designs out yet from the vendors that we're looking at. But I'm very strong-minded towards a multi-airlock type design, including mudroom type designs for anything that we're going to do going in between the habitable volume and outside. So yeah, good stuff.
Yeah, that's a good point.
Very interesting. Yeah. So I'll pose a general question. How can we use the reduced gravity environment, or how can we utilize reduced gravity to understand the effects of materials production, repair, and in situ resource utilization necessary for sustained duration surface operations?
This is Ron again. One thing I can think, the easiest one I can think of is the ability to possibly move large amounts of material around rather easily, to a certain extent, of course, depending on terrain. But just the reduced gravity, potentially we can move more.
Right. So there's certainly a granular materials component here.
And if we're going to get any resources off the moon, the first one I think we're going to get is extracting oxygen through benefaction type processes. And it's most likely easy to do that with the finest grain material that we can get up and sieve probably fairly easy and move into furnaces and stuff like that.
Good point. Suman, oh yeah, your hand is still raised, or is raised. Suman, can you hear me?
Yes, I can. Can you hear me?
Oh, yes, go ahead.
Hey, so thank you, Mike. So because as you rightly mentioned, this is like closely in alignment with the type of the stuff we are also thinking in the complex fluid or soft matter direction. So um, one of the question, instead of telling about the solution, maybe a question might be better posed, which is, I personally feel that in Moon or in any deep space exploration, when we are thinking about making this construction, making ability to make things without water is very important. And for an example, there is a liquid carbon dioxide based processing that current construction practices on Earth they use. So, um, is there any thought process around that? Because and why I'm saying is like I had a background in construction industry. I used to work for a building products manufacturing company, so I know that with regard to cementitious material, there is a time component on Earth. Meaning, when you make things over time, the moisture comes in and they become stronger. That is not going to happen over there, I presume, because it will just evaporate because of lack of vapor pressure. So anything that can utilize without water, I think that will be really, really interesting and important.
Yeah, that's a good point. I don't expect water to be, I mean, there is water on the surface of the moon, but I would imagine that would be used for ISRU, for breathe air for the astronauts breathing, for oxygen, or just drinking water or propellant to make propellants.
Yeah, correct. So that is why any process that is water intensive, which are in our present system. So, for example, when people are talking about 3D printing, etc. So I think that can be a little challenge in my mind. And again, my experience is only up to that. The other part of the problem, I think, is obviously with regard to. So I can give you an example. I heard this a couple of days back. I think we did some experiment in Glen, and again, if I'm misquoting it, uh, I'm sorry, I'm asking for, I apologize ahead. But what I have heard is that they tried to flow some granular media in zero gravity, and it flows perfectly fine. They tried to flow in one, like on Earth, it flows fine. But the moment they go into like a moon gravity, 1/6 of G, and they found like the hopper or this thing start jamming up. So that is, I think, an interesting and important question, both from the viewpoint of in-space manufacturing and for complex fluid granular media type fluid.
Yeah, absolutely. Granular materials experiments are one thing that I need to read up on some more. That's I don't really have a whole lot of knowledge in that area, but I certainly need to. So there used to be a fair amount of granular materials research in microgravity, not quite as much anymore. Well, I can start with some off the wall questions. How could we take advantage of reduced gravity to enable new designs, structures, or materials? Or we could talk about, I mean, to get too detailed, but what scientific insights are required to enable additive manufacturing in space?
Well, it kind of depends on the process.
Yeah.
The deposition process, not the 3D printing process. That's just, that's a mechanism to move a nozzle in 3 dimensions, and you got to deal with the dust. But when you start talking about the deposition process, the materials change significantly, the power requirements change significantly, the ISRU support requirements change. And I kind of got fixated on the water discussion a minute ago, and because we've always wanted to get away from my water-based cementitious material because of the problems it poses in terms of having to maintain some kind of atmospheric control over the process while to let it cure. But there are waterless. Sulfur is a good waterless binder. It's available as a byproduct of oxygen extraction and other chemical processes. Its problem is that it's a thermosetting material at relatively low temperature, and that it sublimates a little bit in the vacuum, slowly, but consistently. So you got to deal with it. And we're looking at alloying. I mentioned this in the chat. We're looking at alloying it to basically to raise the melt temperature with a low level of alloy, and try to stabilize. It'll increase the melt temperature, but it'll also stabilize the vapor pressure, and then we can keep the temperature down by insulating it with loose regolith or regolith bags or whatever that to offset the tensile loading from pressurizing it and provide micrometeorite protection and radiation protection. So there's options there. I'm not sure I answered your question.
No, it's okay. I mean, yeah, your response was fine, is what I meant to say. I threw the word no in there. Me too. I'm sorry. Anyone else have other thoughts, comments?
Good day, Masha is the name. I was thinking about the idea that was brought up surrounding separating them and using that the additive manufacturing process.
I didn't get that question.
The metals from the lunar dust, extracting the metals and using that as a basis for the additive manufacturing and 3D printing process. I know that they mentioned about certain challenges. I think one thing is that could be done is equating negatively charged particles in the whole ionic separation process, and then using that to make the compound a foolproof compound in the 3D printing. It's just like what that for example, the doctors do it. Even doctors do it all the time. I know I'm going to the med side. Like, let's say that somebody gets cyanide poison, they inject the body with cobalt, and then cobalt will infuse with cyanide, and then the body discretes it. So there are ways that you could actually, when you extract it, there are ways you could actually combine positively charged particles with negatively charged particles then to create a compound. It happens within the human body, like when somebody gets poisoning. I know that cyanide is one thing that is used, and doctors then use cobalt, which is negatively charged, then go the positively charged particles of cyanide, and then inject the person with oxygen, which then gives a positive 2 charge, to then revive a person. So I know that chemical chain reactions take place even from a med-sci component. So I know that, also from a medical science standpoint, so I know the possibility exists that it could be done on a lunar. Okay, if we could do it on Earth and it happens within the human body naturally, then we could. And I've seen the unlikelihood of it happening on a lunar surface.
Interesting.
Yeah, I mean, if the problem with something like oxygen is that it's, most of it is tied up as oxides, which are, they're not. It's not individual it's not individual particles that may or may not be charged. It's you got to drive the oxygen off by heating it up, or. But if I got the gist of the comment correctly, though, I mean, it'd be interesting to take advantage of that if you can.
Yeah, it's like combine positive to negative. You have a dipole moment that takes place. I mean, dipole moment takes place all the time, even within. Because that's what doctors use as a common sense to revive a person last minute before death. So I mean, dipole moment is something that could take place, anywhere.
So I'd say that's a good concept, and that's actually what you're describing a lot is some of what ionic liquids employ themselves, but they do it within a salt form. So if you say make this you're saying like thiocyanate, right? Good complexing agent for some metals, right? Well, you can make that thiocyanate into the form of a molten salt at room temperature, and that's a lot of how those processes kind of go about themselves. So it's not a bad thought for sure.
Interesting.
Well, I don't know about you guys, but my head is swimming a little bit in all this conversation. I've been trying to take notes and so I can kind of report out. But that was kind of what I anticipated because I thought we'd have a lot of different backgrounds here, and hopefully we got some topics thrown out there that resulted in a lot of good discussion. I'm not sure what. So. Yeah, I appreciate your. No. I appreciate your bringing up some interesting topics, Mike. I know we're going to. Kyle Bankhead has been taking notes, and myself, we're going to consolidate those over a week or two. I think we get those sent in, and then there'll be a kind of report out of this conference workshop that will be sent, I guess, to every attendee. I'm not sure exactly how that's planned, but I think this session was very interesting. Hopefully, everybody else will find it that way too. I guess it depends somewhat on my writing skills. Since we're closing in on 3:20, I was told that there will be no concluding remarks after this. So when we're done, we'll just shut down this link and that'll be the day. But we will resume tomorrow at 10 o'clock Eastern time. So while we still have a couple minutes, any closing questions, ideas, suggestions?
Question. Lunar surface is exposed to solar wind, unlike surface of the Earth. Solar wind is composed by high energy protons and electrons. Mm-hmm. Sometimes semiconductors are doped by neutrons using nuclear reactors on the Earth. Can solar wind be used to manufacture some advanced quantum materials or dope semiconductors?
Yeah, I don't have an answer to that one. That's an interesting, being mostly ignorant to that, I would have to say, that sounds like an interesting concept.
I think that something, maybe not like we say like for p doping, like a solar panel necessarily, but I believe there's been some thoughts on that in the past. I'm not sure. I'm not an expert in it. I think I've read about some sort of like focusing, like basically like getting basically using some magnetic fields, so forth, to bombard an area. So, but I can't speak too much on it, but I have heard of something like that past being proposed. I can't remember the name of it though.
I was going to say the same thing, Chris. Years ago, we built a high temperature crystal growth furnace that we flew on Space Lab missions to evaluate the effects of low gravity on directional solidification of a number of semiconductors, and I recall that coming up as a potential benefit for long-term future space processing. I'm not aware that it was ever tested in any way, shape, or form, but it's a good question.
Yeah, I don't think I've read of the concept, but I don't think I've actually seen anyone make an actual experimental device or
Yeah.
anything like,
Yeah,
you know what I
exactly.
mean? I just heard it kind of referenced as an idea. So it's an interesting one.
Yeah, yeah.
Yeah, that kind of goes to my question of how can we utilize the lunar environment, or the environment on the surface of the moon to take advantage of that to enable new designs or materials or manufacturing techniques. I mean, that's a bit difficult to conceptualize, but I just, my head goes to, you want to live off the land and you want to thrive in the environment you're given, which we've pretty much learned how to do on Earth. It's certainly a larger challenge to do so on the moon, but maybe we can take some steps to get there.
I'm reminded of the experiments that Alex Ignatius from University of Houston did years ago on the wake shield. Was Bob Hires involved in any of that? For some reason, I'm thinking he might have been, but anyway, the wake shield was deployed from the shuttle, and it basically generated an ultra high vacuum behind it, and the goal was the same, to see if we could grow very pure, defect-free crystals in that environment. I don't really recall what may have come out of that whole research area, but and again, I mean, the vacuum on the surface of the moon, I don't know if it's significantly worse, better, or the same as what it might be behind a wake shield in orbit around the moon, where you could periodically, with lower energy, get up there and pull down samples that have been processed in that environment and do something with them. I knew it was a hot project for a while.
Yeah, I'm not familiar with that one, but it sounds like it would be.
Well, ladies and gentlemen, it's been an interesting couple hours. If there are no other questions, we'll wrap this up, and I will try to start consolidating all these comments and ideas. And I assume this is being recorded, so hopefully all the attendees' names are being recorded as well, and we can put those out there too. And hopefully I can tie comments to names, and if people want to collaborate, they'll be able to figure out who to collaborate with. Mike, appreciate it. Jennifer, thanks for all your help. As always, Chris, good discussions. Thanks to everybody. And we'll talk to everybody tomorrow, I guess.
Sounds good. Thanks for leading this, Mike. I really appreciate it.
All right. Everybody take care.
Thanks, everyone.
Bye.
Thanks.
All right.
You too. Bye.